Hello class, we are doing chapter 4 in journal 1. This is the culmination for us, so we will be doing several applications of derivatives. We've been working all this time, taking first derivatives, second derivatives, talking about increasing, decreasing, concave up, concave down, all that to get to these type of problems. We will be doing, in general, minimization, maximization, or optimization problems. And why that's so important in business calculus is we may want to be minimizing cost or maximizing profit. We'll have a function that's given, and then we can tell, how many units of a particular product to make that would maximize profit. Okay, so we're going to work through some vocabulary first. So in the beginning of chapter 4, we see the word extrema, and there's a couple types of extrema that we need to distinguish between. So suppose I have a function like this. It's a continuous function. And we might ask questions about what are the global maximum, global extrema. They're also sometimes called absolute. And those are as opposed to local, which are also sometimes called relative. Max and local min. Okay, and what these 4 types of extrema mean. So extreme means extreme in either direction, so either a max or a min. And then the easier type that we're going to handle first are what are called local extrema. And those are just bigger or smaller than their neighbors. So like here's an example of a local min. It's smaller when it looks all around, it's smaller, looks to the left, looks to the right. It's the smallest of its neighbors, but it's not the smallest overall on this whole graph. This right here would be the global min. So global extrema are defined either on the entire domain of the function. So if the function begins right where I drew it, ends over here where I stopped over there, or on global extrema also defined on some closed region that is defined, that's given to you. So they might say from, let's say 1 to 10, what is the global min? And the answer would be the same. On this section of the graph, from 1, when x goes from 1 all the way up to x equals 10, right there, that section of the graph, the global min is the same one that we already found. And the global max, it looks like it's just barely a little bit bigger over here than it is over there. So we have a global max. So again, they'll give you a region over which to find global extrema. And then local extrema are these sort of suboptimal. Sorry, that's a local max. And another local max. Okay, so now that we've got our vocabulary, one of the things we want to emphasize that we've already talked about thus far is that the critical points got the adjective critical because their horizontal tangent lines occur there. But because of that, so identify all critical points on this graph. There's one, there's one, there's one, there's one, there's one. It just so happens on this graph that every critical point is an extrema. But had I made the graph, maybe do something like this over here, continue on, and let's say it goes like, here's a critical point. That's not a max or a min. It's not a local max, not a local min, it's not a global max, global min. So the moral of the story there is that CPs are good places to look for extrema, but you're not guaranteed to get extrema. And that's really Fermat's theorem. So that's in the beginning of chapter 4 as well. Read those couple pages. Fermat was a lawyer turned mathematician, and he discovered this property that extrema, if you have an extrema, it must be that it has a horizontal tangent line. It's a critical point. But just because you're a critical point doesn't necessarily mean you're extrema. Okay, so make sure you understand that it doesn't go both directions on that theorem. All right, and now we're going to start tackling some problems to figure out how can we find these local extrema. So again, we're going to divide this into two classes of problems. We're going to deal with local extrema first, and then we'll come back and do global extrema. They have slightly different techniques that are used to solve one or the other. So given a problem, be very clear, find the local extrema for this problem, or they'll be very explicit, find the global extrema for this problem. Okay, so we want to work a couple local extrema problems. Here's the first one we're going to look at. Find the local extrema for this function. It's a nice polynomial, and we know local extrema by Fermat's theorem happen at CPs. They're good places to look for extrema, and then we'll determine if those CPs actually are extrema using the f prime line that we already know about. So let's take our derivative, and let's set it to 0. So let's see, we'll have negative x squared plus 2x plus 3. That's a quadratic equation. We could use the quadratic formula to find the roots of this, or maybe if we're lucky it'll factor. Let's see what happens. So maybe I have a minus x and an x, a 3 and a 1. I just gotta get my signs right here. Let's see, I need a positive 2x, so that means this must be a negative. So negative times a negative will give me the positive, and then this must be a negative. Does that work? Negative x squared, no, that must be the positive one. Negative x squared plus 3x, like that was the minus. Plus 3x minus 1 plus 3 equals 0. All right, I think that factors there. We can set each factor to 0 then. We get these two linear equations, which are much easier to solve. So let's see, that says x equals minus 1. This says x equals 3. We have two CPs. And now we want to check, is this CP a local max or a local min? We'll be able to ascertain that using the f prime line, which is the same f prime line we've already seen from increasing and decreasing intervals. And so we put, just as before, we put our CPs on there in order. It's a number line. We pick a point from each interval and we plug it into the derivative. So I try -2, and I want to figure out what is f prime of -2. I can plug in here or here. I'm going to plug in right here, because I think that's easier, make the arithmetic a little bit easier. So when I plug in -2 for x, I'll get +2 minus 1, which is a positive, times a negative is a negative, so it's decreasing there. Then when I plug in 0, I'll get negative times negative is positive, so it's increasing. And then lastly, +4, when I plug that in, I'll get a negative times a positive is a negative, so it's decreasing. And what this says then is that the intervals of increase and decrease can be read right off this sign chart. But further, and what we want to do now, because we're trying to find local extrema, is I can now say something about this CP at -1. The function actually was decreasing, and then it starts to increase again, and then it decreases again. So it has this general shape. And what it means then about x equal -1 is it has to be, besides just having a horizontal tangent line there, it has to be a local min. So we can add this. Besides just being a CP, it has to be a local min. Similarly, at x equals 3, it is increasing and then it switches to decreasing. So right there, where it switches, at x equals 3, that CP has to be a local max. Again, you can interpret that just by thinking logically about what this sign chart means. You already know how to do the sign chart, it's just a matter of interpreting the sign chart. That's the only part that's new for local extrema. All right, so let's check what this looks like, what the graph of the function looks like. Does it have that shape, and that we do get local extrema at these 2 points? So I'll share the screen and we'll look at a tech tool. Okay, so I've already loaded the function we were given, -1/3 x cubed plus x squared plus 3x plus 1. And it does have the shape that we started with. It is decreasing until it gets to -1, then it's increasing to 3, and then decreasing again. And it turns out at x equals 3, there is a horizontal tangent line there. Furthermore, x equals 3 is the local max. It's bigger than its neighbors. It's not the global max. We can't answer that question yet. We're going to need another technique to do that, but we can say it's bigger than its neighbors. Even though over here is bigger than it is a local extreme, a local max. And this one down at -1 is a local min. On the graph, it also shows you the corresponding y value, but you know how to get that yourself analytically by just plugging in when x equals -1, what is the corresponding y value? When x equals 3, you plug into the original function to get the corresponding y value. Okay, so we'll just do one of those just to show you to get the corresponding y value when x equals 3. That's the same thing as getting f of 3. Which, plugging into the function, we have -1/3 times 3 cubed. So -1/3 times 27 is -9. Plus 3 squared is 9. Plus 9 plus 1. So the first plus and -9 go away, and we just get 10. So this local max then occurs at the point 3, 10. Okay, that's our first example of a local extrema. Let's work a few more. Same instructions, different function. You're going to do this repeatedly this chapter. And sometimes the function will have a story that goes with it, a particular application that makes it of interest. In the beginning, though, we're just going to practice these sort of straightforward ones. Let's try ln x squared plus 4. So we get to practice some more of our differentiation rules, because to find local extrema, you always have to start by finding CPs. So a CP is a place where your first derivative is 0. So we have to take our derivative. Now look in your toolbox, you go back to your notes, go back in the book, pause the video. How do you take the derivative for ln? Well, the ln rule tells you, you take a look at this stuff here, you put it in the denominator, and then put its derivative in the numerator. And then back to our pretest, very beginning of the term, when does a fraction equal 0? It only happens when the numerator is 0. So it's easy to solve this. This just says that the CP is at x equals 0. And now our question is this CP a max, a local max, a local min, or neither? Which is the option. And we do that by doing the f prime line. The same f prime line that we use for intervals of increase and decrease helps us find local extrema. So this little picture right here is like the summary of a lot of stuff in this class. Okay, so I picked something to the left of 0, try -1, plug that into the derivative. So f prime of -1, I'll have a negative in the numerator, a positive in the denominator, becomes a negative. It's decreasing from -infinity up to 0. And then when I try something over here, like a +1, I'll have a positive number over a positive number, it's a positive, and then the function is increasing from 0 on. Okay, so it didn't ask about intervals of increase and decrease though, it asked about local extrema. So what is our interpretation of this critical point at x equals 0? This must be a min, right? Because it went from decreasing to increasing. This must be a local min. Okay, let's work one more in this section. Find the local extrema for this function, another polynomial function. But what do you notice about this one? Which kind of differentiation rules are we going to need for this problem? Well, there's really, maybe I'll put them in brackets, there's really two functions being multiplied together. So I actually need the product rule. Or another way to handle this, to avoid the product rule, would be to cube this thing out. So I'll take a little bit of algebra and arithmetic and then multiply by the x. It's not too difficult to do that, it just takes a little bit of time. Or you can use the product rule. We're going to practice the product rule. So we'll call that the first function, and this the second function. And so we go set up the structure. First times the derivative of the second, plus the second times the derivative of the first. The first function is x. The second function is x minus 3q. That goes back here. Then the last box to fill in, the last box is the derivative of the first function. The first function is x. Its derivative is then 1. The second function requires the general power rule, which says it's just like the power rule, but you go times the power, take the function in parentheses down the power, multiply by the derivative of what's inside the parentheses, which is just a 1 in this case. Okay, that is f prime of x. Why did we take that? Because we want to find the critical points. Those happen when the first derivative is 0. So we'll take the first derivative, set it to 0. The reason we want to find critical points is they're a good place to look for local extrema. Not every critical point is one, but oftentimes they are, and we'll use what we're doing here is called the first derivative test to find those. When we do this f prime line, that's the first derivative test because we're using just the first derivative to find extrema. Okay, so we need to do some simplifying before we can set this equation, or factor this equation. So I'm going to clean this up a little bit. I have 3x times x minus 3 squared plus x minus 3 cubed. And we want to solve this equation. This equals 0. There's some stuff in front of a plus sign, and then there's some stuff after a plus sign. So what I'd like to do is see if I can pull out something that's common to both the before and after the plus sign stuff. And I see that there is an x minus 3 squared in each of those, so I can factor that out. And what I'm left with will be some stuff that was left before the plus sign, which in this case is a 3x. And then there'll be something that's left after the plus sign. In this case, that's one of those x minus 3's got left. You can always check that that works by distributing. You get the same first term, distributing, you get the same second term. By doing that, we can clean up what's inside here. And now we have several factors equal to 0. There's really like an invisible third factor, I guess. Right, we can really say it's like this. X minus 3 times x minus 3 times 4x minus 3 equals 0. The only way 3 things can multiply together and make 0 is if at least one of them is 0. So I can set each of them to 0, and I get this repeated one, x minus 3, and 4x minus 3 equals 0. They're both linear factors. Linear equations are easy to solve. We get a CP at x equals 3, and a CP at x equals, what, 3/4? So now we have 2 CPs to put on our f prime line, and then we'll just check for sign changes. Whenever we have a sign change, we have a local extrema. Don't always have to have a sign change. Remember, we've seen some f primes that look like this. We had a couple CPs. If I had plus, plus, minus, plus, you should be able to look at this and interpret. Let's label those CPs. CP1, CP2, CP3, CP30. So plus, plus, there's no sign change. It's increasing, then increases some more, but then it starts to go back down. So that means this one must be a local max. And then when we went the other direction, we're decreasing and go increasing. This CP must be a local min. So you should get good at just looking at a sign chart and interpreting. That should be a very automatic, straightforward thing. All right, but that wasn't ours. I was just making sure we can interpret that. Ours was, we have CPs of 3/4 comes before 3. Put them on the number line. Pick a point in each interval, plug it into the derivative, check your sign chart. So let's see what happens. Let's try 0 into our derivative. Any line would work, but I think the simplified line, maybe I'll write it down here. The derivative simplified is x minus 3 squared times 4x minus 3. So when I plug in 0 to the derivative, f prime of 0, I'll get negative 3 squared, which is positive, and then minus 3. So I'll have a positive times a negative, that's a negative. Then I'll try maybe 1, seems pretty easy. F prime of 1 makes the arithmetic a bit easier. So I'll have 1 minus 3 is minus 2 squared, becomes a positive number. 4 minus 3 is 1. So positive times positive, positive. One last interval to check. I'll try 4 in that last interval. Plug that into the derivative. 4 minus 3 is 1. Squared is positive. 4 times 4 is 16, minus 3 is 13. That's positive times positive, positive. So here's an instance where we didn't get a sign change on that last one. This one is still just a CP, but this CP gets an upgrade to also be called a local min. Okay, that is local extrema, all with the first derivative test. So next video, we're going to add the second derivative test. It's yet another way to find local extrema. Okay, but you practiced on the first sections in chapter 4.